Alright, AP Chemistry, this is segment 2 of the YouTube lecture. So, we left off here talking about concentration cells just a second ago, so I'm going to sketch again here the cell that I had started describing before I had to cut it off for YouTube's length requirements. Okay, so we have two halves of a cell, both of which are filled with a solution containing silver ions, and into each compartment of this electrochemical cell, we are going to have an electrode. These electrodes here are connected by a wire, and then we also have got a salt bridge here that also connects, woohoo, alright, the two halves of the cell together. So we said that each of these electrodes here is going to be a silver electrode, and that each of the solutions here are going to contain silver ions. We said the only difference here between these two halves of the cell is that the concentration of silver ions on this side is 1 molar, and the concentration over here is 0.1 molar. There's a lower concentration of silver ions here on the right-hand side. Well, this cell here is different from other ones we've already dealt with because each chamber contains the same thing, a silver electrode and a solution of silver ions. The difference is that on the left-hand side, the solution is more concentrated. On the right-hand side, the ion solution here is lower. So what's going to happen here when we link this together, we set the cell up, and we have a go? There actually is going to be, because this is a cell at a non-standard conditions, right? If these solutions were both, say for the sake of argument, these are both 1 molar, nothing at all would happen because the concentrations of ions are the same. But because they are different, okay, this system is not at equilibrium. And so in order to reach equilibrium, what these ion concentrations want to do, basically, is they want to equalize. So there is going to be a reaction. The silver electrode that's in one of these two compartments is going to get oxidized. As it gets oxidized, it's going to produce more silver ions. And then on the other side, silver ions are going to be reduced, and they're going to form silver metal again. So you're going to have this sort of reaction taking place, and this is what fuels the cell. So we have silver plus ions plus silver yields silver plus silver. Now you're saying, oh, Mr. Harper, this looks exactly the same here, well, on both sides of the equation, and it's true, but the difference is here, what's the concentration of the ions on either side? Okay, let's think about it, guys. In order for these solutions, for the concentrations to become the same, what's going to happen? One has to go up, the other has to go down. Well, logically speaking, if we look here on the left-hand side, over here, this is the compartment where the concentration of silver ions is going to have to go down. If these two concentrations want to equalize, this concentration's got to go down, and over here the concentration has got to go up. In order for the silver plus ion concentration to go up in this half of the cell, guys, this silver electrode is going to have to get oxidized. It's going to lose electrons, okay, and we're going to make more silver ions as that goes back. So the oxidation part, okay, is this being oxidized to make more silver ions, okay? So initially, the concentration of silver ions from that part, essentially, is 0.1 molar. That goes over here. Okay, over here, what's going to happen in the left-hand side of the cell is that silver ions are going to go and be reduced to silver metal. And so over here on the reactant side, this starts at a concentration of 1 molar. As you're probably aware, because oxidation is happening here in the right-hand compartment, this baby here is going to be your anode. Over here, this is going to be the cathode. And as the reaction proceeds, electrons are going to flow here along this wire from the anode along to the cathode. So this will be the direction of electron travel over there. Okay, let's calculate here the potential for the cell using the Nernst equation. Okay, so here we go. The potential for the cell is going to be the standard potential for the cell minus 0.0257 volts over N. Well, N for this reaction, guys, how many moles of electrons are transferred? The answer is 1. There's 1 mole of electrons transferred in this process, so it's just 0.0257 over 1 times the natural log of Q. If we look here at this reaction again, Q is going to be the concentration of silver here, and so 0.1 molar over the concentration over here in the reactants, which is going to be 1 molar, and so that just gives you 0.1. So let's plug it in. So this times the natural log of 0.1, and there we go. If we go through here, we calculate the potential here of this cell. It's going to be a very small number, something like positive 0.0591 volts. Okay, so there we go. You can see this is a very small potential. These sorts of electrochemical cells are used for batteries that are very low voltage applications, like for watches or for what have you, things that don't require a whole lot of energy to run. So there you go, guys. Tuck this away. This is another type of cell. It's a subspecies, you could say, of a galvanic cell because the reaction is spontaneous. It is a concentration cell. And this reaction is going to proceed until the ion concentrations, okay, so the silver plus ion concentrations in both halves of the cell become equal. When those concentrations are equal, the system has reached equilibrium and the battery is going to die. So just like good chemistry teachers, galvanic cells never die. They just reach equilibrium. Okay, let's comment here for a few minutes here on the connection between the potential of a cell and the equilibrium constant, okay? As you guys know, okay, we've said that for a galvanic cell, which is what we've studied so far, the spontaneous type of electrochemical cell, we know that the potential, E naught here, is always going to be positive for a spontaneous process, or for a galvanic cell, it always has to be positive. What that means is that when E is positive, K is greater than 1. It favors the formation of products, okay? So for every spontaneous reaction, okay, every spontaneous redox reaction, the potential is going to be positive and K is going to be greater than 1. The reverse is the case. If you have a negative cell potential, K is going to be less than 1 and is going to favor formation of reactants, and so that reaction is non-spontaneous. That is the case for electrolytic cells that we will be talking about in class on Friday, guys. Okay, so when a system has reached equilibrium, or when one of these galvanic cells has reached equilibrium, the potential of the cell is 0, okay? So E for that cell is going to be 0. When that happens, you can prove this mathematically if you want to, but I'll just tell you that the Nernst equation can be rearranged to give you this relation right here. The natural log of the equilibrium constant is equal to N times the standard potential of the cell, which you calculate using your table of standard reduction potentials, divided by 0.0257 volts. So there we go, guys. So if we know, okay, why is this all important, guys? Well, we've talked about several ways in class you can determine the equilibrium constant for a reaction, and here is one that is very useful. If we know the potential for a redox reaction, if we know the standard potential, we can calculate from that the value of K for that reaction, or at least an approximate value of K. So one more way we can find an equilibrium constant. Let's apply this. Okay,